we're going to talk about line shapes. And remember, we have defined our line shape function such that it's a kind of a probability across this frequency interval defined in a way that the integral is 1. What does that mean? That means that if I'm going to use frequency units of wave number, centimeters minus 1, then the units of phi are centimeters. So the integrated area is 1. I can have any shape I want, but I've constrained it such that the area is 1. And we want to know what phi is. We want to know what phi of nu is. And we're going to find that we end up with a Voigt profile in most cases, and that that's a combination of the random motion Gaussian character, which depends on temperature in a certain way, but it's Gaussian in shape, and the pressure broadening, collision broadening contribution, which limits the lifetime that molecules can be in a certain state. That's called lifetime broadening. That type of broadening has Lorentzian shape. So you can show that the frequency dependence of these two primary types of broadening are different. And so since they're different, we can't just add them up in quadrature like we might if they were both Gaussian. We have to combine Gaussian and Lorentzian, and that combined profile is known as the Voigt profile. And it doesn't have any closed form analytical solution except in certain limits. You have to tabulate it. So we're going to end up using a Voigt shape, which is some sort of a marriage between Gaussian and Lorentzian that depends upon temperature and pressure. Temperature because the temperature controls the random motions, and pressure because that determines the collision frequency, which therefore controls the time. Okay, so that's what we're going to do now. And I'm going to end up with some examples of why I care, maybe you should care, about the power of line shapes to get as a diagnostic tool. So we had Beer's law, and remember the key thing is that the optical depth here, the spectral absorption coefficient, when I say K nu is the spectral absorption coefficient. It's at nu. That K is given by the product of the line strength and the line shape factor. So if we had units for S of centimeters minus 1 per second, then units of phi are in seconds, and the seconds go away, because K is centimeters minus 1. So you always have to be careful about the units. But K is S phi. And remember now, if we integrate K, if we integrate this over frequency, that term goes away. So S is nothing more than the integral of K nu d nu. There it is. So you can think of it different ways, but the line shape function is really the ratio of the local lines spectral absorptivity divided by the integral. Okay, that's the line shape function. And again, there's these alternate forms that we have to pay a lot of attention to watch the units. For frequency, there's really only two. It's either hertz, that is per second, or wave numbers. Therefore, that should have been a nu bar. And they're just related by C. So you can go back and forth between frequency units by multiplying or dividing by C. And you always pick units. You just have to pick units that are consistent with the frequency units you're using in your spectroscopy. S has different units. We've talked about that. There's a lot of different forms. In the infrared, we tend to use centimeters to the minus 2 per atmosphere. But of course, K doesn't know anything about this. You can get to K in a different way. So however you do this, they have to be equal. But if you do it in centimeters minus 2 per atmosphere, it has this form down here. I'm dividing by pressure in atmospheres. That's pressure of the absorbers. What's P? P is equal to NKT. But when I have pressure in atmospheres, I have to have NKT in dynes per square centimeter, and then I've got to divide by 1.013 times 10 to the 6th. So there's always these little unit issues that you have to pay attention to. That's what this is here. Just a reminder of how you go back and forth between pressure in the CGS system and pressure in the atmosphere system. I don't know who decided that you should be centimeters minus 2 per atmosphere. I learned it from Professor Penner and his book. Actually, I learned it from his book. I don't know whether he started it or not. Okay, so where do these come from? So if you knew A, you can calculate the A coefficients, you can calculate the intensity, the line strengths. How do we get phi, for example? Usually it comes from measurements, high resolution absorption measurements. So somehow you do an experiment in which you actually measure the shape of this line. And then you use Beer's law to invert it and convert it from transmission to the spectral absorption coefficient. What's the area under that curve? The area under that curve would be it would be S. But the shape is what I'm after. And so you can take that local value of K and divide it by the integral and plot it now as phi. Now the integrated area under there is 1. So that's how we get it. We measure transmission in a high resolution experiment, convert it to absorbance, divide by the integral the area, and we now have shape. And in this system, we frequently will identify the full width at half maximum or the half width at half maximum. You have to be careful about this factor of 2 floating around. People use when they say the half width, they're only giving you half the information. Is it the half width at half maximum or the half width at full maximum? Or full width at half maximum. That's a problem. You have to be careful. This is usually expressed for collisions. It'll be expressed in terms of a parameter gamma for the half width per atmosphere. I always like to use 2 gamma because then you know I'm talking about the full width. But unfortunately, it's not fully standardized. So that's where we get it. Now, I'm going to review some of the primary types of broadening, which really fall into 2 categories. The first one is called natural broadening. It comes to us from the finite lifetime, the radiative lifetime that we've been talking about. And there's collisional broadening. It comes about because of the finite lifetime that it spends between collisions. When you increase the pressure, you increase the collision frequency, you decrease the time that it spends before it has a collision, and you decrease the time that it's there, and that brings with it an uncertainty or fuzziness in the energy of that state, and therefore results in line broadening. These 2 effects are basically associated with the limited amount of time that a molecule spends in its quantum state. It's called homogeneous broadening because it affects all of the atoms and molecules equally, independent of their random motion velocity. It's called homogeneous broadening. And you'll show, I'm not going to show it very well, but I'm going to show you that the functional form, mathematical functional form of this broadening is Lorentzian in shape. You'll see what that is. The other primary type is called Doppler broadening, and this is associated with thermal motion. The Maxwellian velocity distribution is Gaussian. So it's no surprise that the shape of absorption line is Gaussian. It's a manifestation of the Maxwellian velocity distribution. That form is Gaussian. It's called inhomogeneous broadening because it affects different classes of molecules, that is, different speed classes, differently. Now, these are just some general terms. Lorentzian, Gaussian, homogeneous, inhomogeneous. And when we put those things together, we get conventionally a Voigt profile. Voigt is a mathematical function. There are some improvements on this that come into play. We're not going to talk about them. So we're going to treat the broadening of collisions to be independent of their velocities. We know that's an approximation. So one improvement we could make if we had the time would be to go to a speed-dependent flow product. And there's another one called Galatry profile. So there are some refinements, but some people will just use one or the other. That is, they use the Lorentzian or the Gaussian. But increasingly we use the Voigt. It's a combination. Why? Because they kind of both are important. We're not really close to being in the limiting case where one dominates. Well, let's look at the natural line broadening as a way to help us understand this. So if we have an upper level and a lower level with a probability of a spontaneous transition A, so that the average lifetime is tau, energy spacing h nu, then you can invoke the uncertainty principle up here that relates the uncertainty in time to the uncertainty in energy in terms of h over 2 pi, or that's Planck's constant. So the uncertainty in this energy would be given in terms of the uncertainty in its lifetime, and you get this result. But we have to be a little bit careful. This state has some uncertainty too. So in fact, you have to kind of average those out. So the uncertainty in frequency units would be the uncertainty, combined uncertainty in the two levels, which would be 1 over 2 pi times 1 over the lifetime in U and the lifetime in L. If L is the ground state that has no emission possibility, then that term goes away. So roughly speaking, delta nu is 1 over 2 pi tau. It's a question of whether there's another factor of 2 or so in there. That's called natural line broadening. Natural, independent of collisions, so natural. Now, if we look at electronic transitions, these are the ones with the high A coefficients. So if I told you that tau is 10 to the minus 8th, what's A? 10 to the 8th. They're just inverse. So if high A factor, short time, leads to some certain amount of broadening, 10 to the 7th hertz. So that electronic transition has a broadening coefficient of 10 to the 7th hertz, or in wave number units, it's 10 to the minus 4. If we go to the infrared and look at a vibration rotation transition where the lifetime might be, say, 100th of a second, that corresponds to 10 to the minus 10th wave numbers. So what does that say? That says that, boy, that the natural line broadening in the infrared is pretty negligible. But we really have to compare these with the other types of broadening to see whether or not it's negligible. But they are typically much smaller than the Doppler width and the collision width I'm going to introduce now. So when you have lifetime broadening, that is limited by the length of time that is in a state, limited by the uncertainty principle, you can show, or the book that you read can show, that is a Fourier transform, that this is the shape. So this is the so-called Lorentzian form, that phi is 1 over pi times the full width at half maximum divided by 2, full width at half maximum divided by 2 squared, plus the distance from line center. So that's the behavior of this function. The area is 1. Here's the width, delta nu n. That's the full width at half maximum. And you can switch units if you want to. So basically, this tells you how phi varies with frequency. Frequency difference, distance from nu 0. It goes like distance squared. So it goes 1 over the distance squared. Whereas the Gaussian is going to fall off with an exponential form. So I'm going to just show you this slide here. It's in my notes. If you want to really follow this, the reference I suggest is the book by Demtroder. And so this is an oscillator. It's a vibrating, oscillating molecule, and it's damped. And so this is the differential equation for that behavior. And there's a damping constant gamma. And if you have a big value of gamma, it damps faster. And that damping is related to the lifetime. So there's an average lifetime, but if you have a distribution of lifetimes, then you can represent it in this way. And that leads to this, this in Fourier analysis, leads to this functional form. So I won't spend any time on that. If it has a longer lifetime, you can specify energy more tightly, and the line width gets narrower. So there's a mathematical formalism that leads to this shape, which is Gaussian, Lorentzian. Lorentzian, L. Now, more important than the natural broadening is collision broadening. And so now, if you've had kinetic theory, you'll know that we can talk about collision frequencies in terms of kind of a hard sphere collision frequency idea. We imagine a big molecule B more or less sitting, not moving around too much, and some small molecules A coming by, or A's being fixed and B coming by. So you talk about the volume swept out as B moves through this space, and it sweeps out an area, sweeps out a volume that depends upon the area of this cross-section and the velocity. So this has to do with the size of this region, and it's terms of hard sphere cross-sections, they're called, or optical collision diameters. If we're doing transport properties, you'd use kinetic theory to describe the thermal conductivity or the viscosity. But we're talking about line broadening. So instead of calling it a hard sphere diameter, I really should call it an optical collision diameter, because it's going to be the number that corresponds to the collision frequency that causes broadening. And so when you define different terms, you actually get slightly different numbers for the cross sections. You have to be careful about this. The broadening, the optical collision diameter is not exactly the same one that you would use to match the viscosity or the thermal conductivity. You have to be a little careful. But it's a way of thinking. And what we talk about is, well, how often does this B have a collision? How many collisions does it have with all of the A's? So you imagine you're a B and you're going through space and you're occasionally hitting A's. How many do you hit? Well, it depends. You have the volume that you sweep out, which is this pi sigma squared, times the speed, which is c bar on average. And then you say, well, how many A's are there in that volume? Well, there's an n sub A, number per unit volume. So that's how many collisions that an individual B has per second. And you can do this for mixtures, and you can expand the space, so you can study that. But the point is, the collision frequency, collisions per second, depends upon the density. Now, I can rewrite this density as N is P over KT. That's why it's sometimes called collision broadening, sometimes called pressure broadening. But you also see that it has the square root of T dependence in it. It's usually written, the collision frequency is usually written in terms of mole fractions, total pressure in dynes per square centimeter, square root of T in here. So this has the same lifetime limitation as the natural broadening. Collision frequency is the inverse of the average time that it spends in that state. So you can write this expression in terms of pressure, mole fraction, cross-section, and 1 over c bar. Now, we have to be careful because we do have this happening in the upper state and the lower state. So we get the 1 over 2 pi, but now we have to take the tau. And so in the limit that the collision frequencies are the same, these two terms are equal and 2 goes away, and I get collision frequency over pi. So in seconds, the full width at half maximum collision frequency, which is going to turn out to be what we need, is written this way. Now, frequently in the literature, the collision broadening frequency is given in terms of a parameter 2 gamma. So 2 gamma is just some combination of these terms. So what's tabulated in HITRAN and other tabulations is the collision broadening coefficient per atmosphere. And so what you have to be careful about is sometimes it's 2 gamma and sometimes it's gamma. When you see 2 gamma, you know that you're talking about what will be the full width. And this one has the Lorentzian form, just like we showed before. And so where this shape, distance from line center squared plus delta nu c over t. So delta nu c is the total, is this number divided by 2. And that delta nu c comes from here. So you tell me the mole fractions of the species, pressure of the mixture, and the individual 2 gammas, collision broadening coefficients, I can calculate delta nu c, use it here, and I've got my line shape function. Roughly speaking, how does 2 gamma depend upon temperature? Well, because it's usually given at 300 degrees. Roughly speaking, it's inverse with temperature by an amount that's 1/2 square root of T if it's hard sphere, but now you have to measure it. And when people measure it, they find out that instead of a 0.5, they get numbers between 0.6, 0.7, 0.8, 0.9. That's a measured quantity. And that's because it is not exactly a hard sphere. Here's some numbers. Collision broadening of CO. And this is for, let's see, this was an example for a particular transition of the second overtone of CO and air, 300 degrees, 1 atmosphere, and so on. So you can evaluate this. And so this was an example in your notes that you can look at that shows how you work with the mole fraction and the broadening coefficients to get the final result. What do you notice? The full width at half maximum tends to be about 0.1 wave numbers. Remember we had on an earlier slide something like 10 to the minus 4, 10 to the minus 5, 10 to the minus 10. So all this is telling you is that collision broadening is the dominant form of broadening, of lifetime broadening. And here's some examples here of different wavelengths and species and some broadening coefficients. So let's see. Here's NO. NO is an interesting one. That's in UV, and the broadening coefficient is around 0.14. That's wave centimeters minus 1 per atmosphere. This is at 2,000 Kelvin. Whereas for OH in the UV, it's quite a bit smaller, 4 times smaller, NH. So these are things you have to measure or you can estimate, but they're Lorentzian. So now we have Lorentzian term under control. What about the Doppler broadening? Moving molecules see different frequencies. So the frequency you have to send in to be absorbed depends upon the motion of the molecule. And that's what this is all about. So that Doppler shift is the same as the one you would have been exposed to in college physics. That the apparent frequency is the actual frequency modified by the speed. That effect leads to a Gaussian distribution because there's a Gaussian distribution of speeds. So Gaussian. So it's no surprise you end up with this function. Remember, it's Gaussian and the area is 1. So, and you can relate this to some width. Now the width is the Doppler width. And the Doppler width has got this expression, kT log 2 mc squared. So it depends upon the mass of the moving particle, speed of light, and nu zero. So it's got some, this is the way I remember it. Delta nu d is 7 times 10 to the minus 7 nu 0 t over m. M is the molecular weight, grams per mole. So it goes up with the square root of t and it's proportional to nu 0. So this is important. So nu 0 in the ultraviolet is a lot higher than nu 0 is in the infrared. So the Doppler term is weighted by nu 0 and goes as the square root of t. Whereas the Lorentzian term is kind of inverse with t and proportional to pressure. So you have to kind of weigh all that together. And now, if you're a plasma person, you might be interested in Stark broadening. I'm not going to talk about that. That is a different form. Sometimes you have to worry about instrument broadening. So for example, what if you're watching a flow of gas go by a narrow window and the gas is going at 10 kilometers per second? Maybe it passes through your observation window in a short time. You're only allowed to watch it a certain length of time. That also causes broadening. So it only happens at really high speeds, but sometimes you can have transit broadening. That's this one. There's another kind of broadening you have to worry about. That is, if you send in a really strong laser, you distort the populations, and you have to go back and revisit some of the things we've done. And that's called saturation broadening. Usually you stay away from that. So if you're using an instrument that has insufficient resolution or you have transit, there's a lot of reasons why your lines will appear broader than they might really be. You have to be careful. Here's the example of transit time broadening. So here's the gas that's moving by my laser beam of width d. The time it spends there is d over v, and that corresponds to a frequency uncertainty of v over d. So if v is really high and a d is really small, you can get some significant transit time broadening. But it's got to be going really fast over a small width. Usually doesn't come into play. Okay, I'm going to give you some examples. This would be, okay, we'll do an electron. So the temperature is 300, pressure is 1 atmosphere, M is 30. Electronic transition at 600 nanometers. You know, you C equals lambda nu to get the nu, the frequency is 5 times 10 to the 14th. So that's enough information to get the Doppler width. Remember that 7.17 nu 0 square root of T over M. If I put those numbers in there, I get a number of 0.04 wave numbers. Collision broadening. I need the pressure, I need the temperature, I need 2 gamma. Looks like I didn't give it to you, but it's approximately 0.1 because we're at 1 atmosphere. So what do we find? That the Doppler width is 40% of the collision width, but they're both significant. I can't neglect one or the other. Now if we go to the vibration rotation instead of electronic, now the frequencies are 10 to the 13th instead of 10 to the 14th. I see the Doppler width has gone down by 10. It's gone down by 10 because the frequency has gone down. The collision width is still about the same. It is the same. Now all of a sudden the Doppler width is the negligible one. So whether or not you can neglect one or the other depends on the pressure and the temperature. At combustion conditions of combustion temperatures and atmospheric pressure, you have to consider both, usually. But you can be in a, if it's a fairly low pressure, really high temperature combustion, it can be Doppler dominated. A plasma, low pressure plasma at high temperatures, usually Doppler broadened. So why do we care? Because if it's Doppler broadened, you already know the line shape function. If it's collision broadened, you already know the line shape function. If it's in between, we have to invest in the Voigt profile. Here's another example. It's higher temperature, 1 atmosphere, so basically we just kick the temperature up by a factor of 9. So the temperature is up by a factor of 9, so I'm going to multiply this number by 3. And this one goes as 1 over T to the half, so this one goes down. So now, by going from low temperature to high temperature electronic transitions, they're still both important. I've changed which one is the dominant one, but they're still both important. If I go over to vibration rotations, the Doppler width is now comparable to the collision width. So in these domains here, except for this domain, you usually have to consider both. Doppler broadening is most significant at low P, high T. Collision broadening is most significant at high P, low T, and large lambda. Mostly you have to do both. Okay, what's the Voigt profile? So the Voigt profile is defined in terms of a parameter called A, which I'll show you in a minute, which is a measure of the relative influence of collision broadening and Doppler broadening. It's a ratio. I should have had it down here. Maybe it's on here. Let's see if I got it here. No. Okay. When A is 0 is pure Doppler. When A is big is pure collision broadening. So there's the Doppler waveform. As I increase the relative role of the collision broadening, I bring this peak down because I have to have area out on the sides. The Lorentzian falls off slower than the Gaussian. Lorentzian falls off slower than the Gaussian. So when I increase A, which is the role of collision broadening, it's basically the ratio of the collision width to the Doppler width, not exactly. So it makes quite a difference. The area is 1 in all cases. I'm going to show you the Voigt profile and then I'm going to remind you that there's some other things we have to worry about once in a while called pressure shift. So here's the review. If we have the Lorentzian, it's found this way. You need to know these broadening coefficients. They roughly go like 1 over root T. Typical value is typically around 0.1 at room temperature. And these are homogeneous broadening. Doppler broadening. This is the review panel. It's exponential, e to the minus nu 0. Doppler with 7 times 10 to the minus 7, square root of T over M times nu 0. typical values are shown, and it's inhomogeneous broadening. Now, it's a subtlety at what point you have to pay attention to whether it's homogeneous or inhomogeneous. We kind of usually sweep that under the rug. It comes into play when you have saturation broadening. Okay, so here's our comparison. Here's a pure Gaussian, here's a pure Lorentzian that both have the same area, 1. So notice that they have the same half width. So this is drawn that way. So you can draw them so they have the same width, but they have a completely different shape. All right, I'm not going to tell you about it, but there are some refinements called collision narrowing and galactic profiles and stark brightness. So these are extensions of what I'm going to tell you about. Voigt profile. This is where the physical argument comes into play, that kind of a little hand waving. The physical argument is that these effects are decoupled. That's like saying that the collision frequency of every particle class is the same. They're not. But if you do this, if you say that they're decoupled, then you can combine these two line shape functions and say that there's the Doppler one that depends upon velocity u, and now you have to take the homogeneous one to depend on v minus u. So that's like saying that each velocity class has the same collision frequency, but you got to pay attention to the non-resonance. So u is the integral variable, and u is the frequency of interest. So when you do this, you end up with a line shape function that is a complicated integral. And it's called the Voigt function. So this is the Voigt line shape function. And this integral right here is tabulated in different domains. There are simplifying analytical forms. I should have had this sooner. What is A? A is the ratio of the collision width to the Doppler width times the square root of 2. So it's roughly the ratio of collision width to Doppler width. Big A means big ratio of collision width to Doppler width. W is this dummy variable in the integral, which is the distance from line center, normalized by Doppler nu d. And Y is another variable in this integral. It's integrated out. So this is a number. What does it depend on? It depends upon A and W. So if you tell me A, I can calculate the line shape function as a function of W, which is the distance from line center. You'll see this. Okay. So the trouble is it doesn't have a closed analytical form. You got to calculate it. I'm going to tell you how you would do this. So you want the Voigt function as a function of V, and it's the product of the term out here is dependent on the Doppler term modified by the Voigt function. How do I get the Voigt function? So there's only certain places where it has a simplifying analytical form. 0 here means W of 0. That means that it's the line center. W is the distance from line center. Only then is the Voigt function have a specific exponential complementary error function waveform. Other than that, you've got to go to a tabulation. So the tabulation is going to give you what you need. And here's the table. So you either have this for yourself or you calculate it. So up here is A is across here. W is here. W of 0 is line center. That's line center. Distance from line center is 0. Crossed here is increasing collision broadening over this range. So the way you proceed is the following. You have to know temperature, molecular weight, line center frequency, pressure, cross-section, or 2 gamma. You desire the line shape function. First, you compute the Doppler width from that 7.17 times square root of T over M times nu 0. You get the Doppler width. Depends on temperature. Then you have to get delta nu C. You get that by looking up the values of 2 gamma at that temperature and the mole fractions, and you calculate that. That lets you calculate A. So for this line shape function, A is fixed. The variable is W. So now what you do is you pick a W and you come out with the value of phi over phi of Doppler. So anyway, you go through these steps and you can automate it if you want, but you end up with phi as a function of frequency. Let's see. Okay, what have I left out? I left out the fact that there's a subtle thing called pressure shift. So not only does the width of the line change with collisions, there's a higher order effect that causes the center to shift. And this is a complicated thing to explain. It has to do with the potential functions and their difference between the two states. So just know that it exists. It's expressed in the same form that collision broadening is, as a multiple of pressure over the mole fraction weight of the shift coefficient instead of the broadening coefficient. And when you look this up, it's also available. And what you'll find is that this delta is usually much smaller than 2 gamma. But it can be significant. When's it significant? If you have a narrow line, a fairly narrow line, and you're trying to, you think you're at line center, but the pressure causes the center to move, you're not at the center anymore. So you have to be very careful if you're measuring species that you know where you are on that line shape function. We have to worry, it's usually a small effect, but we worry about it. The Doppler shift. This is just this cartoon that shows you. So if the effective Doppler shift is proportional to U over C, U as being the velocity of the particle along the direction of the laser beam is the only one that counts. So here's the absolute vector of velocity. So you have to have V cosine theta is the component. So the shift in velocity goes as U over C times the frequency. So what you see is that the line gets shifted. Now this one can be observed. We use this to measure velocity. I'm going to show you in a minute. So okay, now I want to show you how we make quantitative measurements recognizing the role of the line shape. So we want to make species concentration and pressure measurements. How would we do that? We would tune our laser, do an absorption experiment across the line, convert the fractional transmission to absorbance, alpha, plot it versus frequency, integrate the area, and that integrated area is SP chi L. That's the line strength, partial pressure right here, and the path length. So if we measure this, and we know the length, and we know the line strength because we know the temperature. This one depends only on temperature. And we know the pressure, we've just solved for the mole fraction. That's how you solve for mole fraction. And by the way, when you do it that way, it's independent of the line shape as long as you integrate it over the line shape. But if you're going to park it at line center so you can make fast measurements, then you have to know the line shape function. How can we get temperature? Get temperature multiple ways. You can get temperature by looking at if the Doppler broadened, you can look at the width. But that's the square root of t, so that's not a good thing to do. Or you can use the two-line ratio and take the ratio of these two lines. So you can look at the integrated area for two lines, take the ratio, and that depends only on temperature, independent of line shape function. So in this case, we recognize the role of the line shape, but we cancel it out by integrating over the line. So let's see. I'm going to give you now a few examples. I'll give you a few examples. This is an example with sodium. Remember, sodium is an alkali metal. The first column of the periodic table, very high oscillator strengths, very high values of A, very strong absorber. Imagine an experiment where we've got some heated sodium in a heated cell. We want to know how much sodium there is. We observe the line at 589 nanometers at 1600 Kelvin, 1 atmosphere. We measure the attenuation as a function of frequency, convert it to K. Remember, I over I 0 equals e to the minus K nu L. Convert that back to K nu, plot it, and look at the line shape function. We get the shape, or we could do the integral and solve for the pressure. So You can get the total amount of the sodium, or you can use it, or you can look at the line shape and try to learn something about the temperature if you didn't already know, or you can just solve for pressure. So you can integrate out the line shape, or you can use the line shape. You have to decide what you want to do. This is very sensitive. So the pressure would be the peak absorption coefficient here divided by SV. So you can measure parts per million of sodium without any trouble at all, probably parts per billion. I had a student who was studying ArcJet, which is a electric propulsion device. And he used this idea to measure the velocity of hydrogen. I wonder if I have a sketch. Here's the sketch. He had an electrically heated hydrogen tunnel expanded out, and the question is, what's the velocity of coming out? We sent in laser light so that's opposed to the flow, and we captured the fluorescence at right angles, and we spectrally resolved the fluorescence as a reflection of the absorption spectrum, and we measured the shift. Let's see if it's on the next slide here. No, it's not on the next slide. So he measured the Doppler shift of 0.7 wave numbers and found that the velocity was 13,800 meters per second, 13.8 kilometers per second. We have used this Doppler effect to measure velocities up to 15 kilometers per second and down to a few meters per second. So the Doppler shift is really a powerful idea. Yes?
When you're measuring in a few meters per second, I feel like it would be very difficult to even know if this is noise or the actual.
Exactly. Well, that's exactly correct. It took a lot of work. And I'm going to show you one of the results we did. So this is easy. The shift is so big that it's greater than the line width. When the shift becomes a small fraction of the line width, it starts to get hard. And we have to play tricks. So we have a few tricks. Anyway, when we played with the tricks, we can get down to a few meters per second. But it's really not the best way to measure low velocities. But this is a good way to measure high velocities. I had another student who did a measurement in nitric oxide. He had a 0.5% NO nitrogen nozzle, and he expanded it out in a free jet right here. We did this in a vacuum chamber. And we used a laser which provided us some radiation at 225 nanometers where nitric oxide absorbs. And we had a special laser that another one of my students built that could be tuned in wavelength rapidly. So it's a monochromatic laser that can be rapidly tuned in wavelength across the absorption line. And we send the light in at some angle, and you capture the fluorescence at right angles. Remember, fluorescence is the light that's re-emitted after absorption. So we're really just measuring the absorption line shape. So here's one of these is shifted and one's unshifted. Here's his results. This would be a plot of his absorption coefficient, absorption versus frequency. And you can see one is shifted and one isn't. Shift was now in gigahertz. One wave number is 30 gigahertz. So he could see it. And now this what's clever about this is he was hungry. He wanted more than the velocity. The shift of 2.07 gigahertz, now what is he doing? He's looking at different angles. If you looked at right angles, there's no significant, and the center line, there's no significant Doppler shift. So this is the difference between looking at two different angles. The shift gives him the axial velocity. What are these two different lines? They're two different transitions. The width of each one of these things also depends upon temperature. The relative heights also depend on temperature because we're probing two different states. So one, and this is subtle now, one depends upon the kinetic temperature, and the relative population depends upon the rotational temperature. In a low pressure expanding flow, you can have different temperatures. So let's see what he predicted here. He He inferred 156 when he had calculated 159 degrees. He measured the pressure, he measured the velocity, got the Mach number. So this was a very powerful scheme for looking at different properties. So the line shapes depend upon environmental parameters. The line shift depends upon velocity. So you can use the shift to get velocity, you use the shape or the relative heights to get temperature, even when there's different temperatures in the problem. And of course the integrated area would give you something that might have to do with the number density if you could calibrate your fluorescence scheme. So this is a pretty powerful idea. And let's see, this is my last example. Let's see. We did this in a hypersonic shock tunnel with test times of milliseconds, and we could observe in water vapor the rotational temperature, the translational temperature, the velocity. The velocity in that case was like Mach 16 or Mach 20, I think it was, something like that. This was an interesting example. We've actually done more since then. This was a student who wanted to use this idea in the inlet of a full-scale engine on the ground. And we had the goal of, could we measure the flux of air coming into this engine? And would that method be equal to or better than using a rake of pitot probes, which is how they do it. So what we did is we take this laser and we split it and we put one beam this way and one beam this way. So one of these beams sees a Doppler shift in one direction and the other beam sees the equal shift in the other direction. And by looking at the relative shift between those two lines, we get the velocity. We did this with oxygen, which has a weak absorption structure near 760 nanometers. Here's the R branch, the P branch. So we looked at one of these lines and we looked at the shift. Now here's where the trick came in. Because the velocities were lower, we didn't just look at the shape of the line. We looked at what's called the 2F spectrum. So we modulate the laser and we do what's called 2F over 1F, and you can emphasize the shifts a little bit more. We could measure smaller shifts and get the noise down. So when we did that, let's see, we did this for Pratt & Whitney, must have been about 5-6 years ago. But it's big experiment, control room. You only have a few hours to set up. It's expensive to run these tests. We were just piggybacking. It worked pretty well. Let's see. This was first we did this at, first they ran through a sequence of tests with time in minutes where they bring in different velocities. They're ramping through a test. They have what's called a bell mouth that they put on the front of the engine that gives a smooth contour of air coming in. Here's our measurement right here. So we measured the velocity as they ramped up in time, and they wanted us to get the mass flux. So we have to get the density, and the density and the velocity gives us the mass flux. Oops, looks like I didn't show you the results. Bottom line is this worked. Our goal was to try to measure the mass flux to within about 1%. We were within about 1% of the pitot system. I couldn't show that it was better. Pretty hard to do, yeah.
Wait, you measured the density as well as the velocity?
Well, you know, density is from known mole fraction of water. So we measure the absorption of the oxygen line, and we can tell you the density of the oxygen. We invoke the known mole fraction of oxygen and air to get the total density that's entered. So we measure on oxygen, but then we convert it to air. So, but that's pretty amazing. This was several years ago. The minimum velocity here was around 35 meters per second, in contrast with 14 kilometers per second. But more recently, we did this for NASA Langley, and we got down to a few meters per second. So it's possible. Now, we've made some assumptions about uniformity that are a little tricky. But anyway, the Doppler effect. It's both a problem and an opportunity. It's there. You have to recognize it, but sometimes you can exploit it. Okay, I think that's. So we've covered a lot of ground today. We did polyatomics. We introduced you to line strength, Einstein factors, line shapes. Now we're going to go back to some serious spectroscopy and how we deal with electronic transitions. It's a kind of a much more advanced subject. but we're going to do that next. Questions? Yeah?
I am interested, I am curious about the pressure shift that you mentioned.
Yes.
Is the physical explanation for that?
Okay. It's a little, let's see if I can explain it. There's always a lower state and an upper state, but we're drawing these energy levels as horizontal lines. But in fact, molecules are undergoing collisions all the time. And so there's some attractive forces, there's a kind of an effective potential function. And when those functions versus internuclear spacing differ, you get an offset. It's a small effect, but it's there. Interestingly, sometimes it's plus, sometimes it's minus. So it's a known thing. It has to be measured. It's often negligible, but if we were to go like 10 atmospheres, we got to worry about this. It's less than the broadening, but it's there. How do we know it's there? Well, we scan it, typically to avoid this problem, we'll scan the laser in wavelength and we'll find the peak. We don't actually care exactly what the frequency is. We just want to be sure we're at the peak. So the problem is that it shifts the peak. And if you work at fixed wavelength, you may not be at the peak anymore. So we have to worry about this. But usually we can kind of work it out. So it's the difference between the influence of the so-called potential surface for the upper state and the lower state. And when that's why sometimes it's plus and sometimes it's minus. It's usually less than 10% of the broadening coefficient.
If the velocity of the Doppler shift is usually any seeding, we can just use the gas.
That's the point. There's no particles.
So
Seedless.
but it's also a point.
What?
It's also it can have the point.
Well, the measurements, it can be a point if you use fluorescence detection. It can be a line if you use absorption detection. If you use absorption detection, you have to make some assumptions or know something about the uniformity. But usually you're measuring the core at high speed. So there's no particles. It's especially for very high speed flows, high temperature flows, no particles. Could be oxygen. We've done it on water, sodium, hydrogen. It's a universal idea. Well, if you, PIV, particle, is the simpler, powerful way to do low speeds and multiple components of velocity. So our method only gives one component in the one I've shown you. So ours is best for when you really don't want to use particles, or the particles aren't there, or the speeds are high. You know, each method has its benefits, but we don't have to add any particles.
I mean, applying the Doppler shift would be used much less.
Well, people do use motion of the particles. Now, you could use Doppler effects, or you could just use transit. You know, for the most part, particle velocimetry is just kind of motion of the particle. Yes?
If you're going to ignore, say, either the Doppler broadening or the collisional broadening, how large of a, like, how many orders of magnitude difference do you generally have?
Well, we rarely ignore it. It's just that you'll read a lot of papers in literature and they'll say, we use a Lorentzian line chain function. Why did they do that? I guess they weren't comfortable with the Voigt profile because, you know, Lorentzian is a closed form solution. So people have, in the literature, there's a lot of people who just take the easy way out. They'll just do the Lorentzian or the Gaussian. You can always ask how big of an error there is by looking at the Voigt function. You can see if you're in a regime where you can neglect the other term. You know, if it's really high pressures, or actually if it's really high temperatures and low pressures, it's going to be mostly Doppler. But why do you care? I mean, the Voigt is not that hard. It's just, you just have to use it. Now it gets tricky if you're in a regime where you have to worry about some other effects that I haven't told you about. Collision narrowing. Dickey narrowing is called. There are some regimes, low pressure regime, where Dickey narrowing. Maybe you're at a pressure, if you're at a low pressure where the mean free path is of the order of the wavelength of light. This is where it happens. So what that means is that you're looking at some molecules and they don't spend long enough in that state of velocity. So if you're a fast-moving particle and you have a collision, on average, you're going lower. So you can't really argue that they all have the same velocity distribution function. So you get some narrowing. The extreme velocities are pushed to the middle. So you're looking at this sample, and you don't really see the right number of high-speed ones because they're being made more ordinary. So that's called, and so the profile gets a little narrow. So you start off low pressure, it's pure Doppler. As you go up in pressure, causing some collisions, which cause the mean free path to kind of get in this nasty range, the Doppler profile actually starts to get narrow before it gets wider. It gets wider because of collision broadening. But it starts off pure Doppler, narrows, then gets bigger. That regime is tricky. That's called the Dickey narrowing regime. So you have, you hardly ever have to worry about this, but it can be there. And then there's this thing called speed-dependent broadening. So the French are especially good at these line-shaped things. They've really developed a lot of nice theories. But the mathematics gets really nasty. So the Voigt is a good compromise. It counts for most effects. Stark broadening is a little different. So if you're a plasma person, now you got to worry about some other effects. I'm kind of ignoring those right now. Any more questions? Okay, I guess we're done for the day. All right, see you tomorrow.